This is problem 4-39E. It's on page 235, and the problem statement is on the left on page 234. The indicated figure shows a portion of a shaft from power transmission equipment. Compute the maximum repeated torque that could be safely applied to the shaft if it is to be made from ASI 1141 OQ2 1100 steel. The problem statement is for multiple pictures, so I changed the words a bit to indicate just our problem. Anyway, let me jot down AISI steel, and it is OQT 1100. Okay, so there's the particular material that this shaft is made from. Of course, you need to reference the figure on page 235. It's figure P439, so make sure you're looking at that because there's geometry information given there. Now, on the left-hand side is the smaller section of the shaft, and we're supposed to find, let's do this, the maximum torque that this shaft could take. Well, at first glance you might look at it and say, well, it's just limited by the smaller section of the shaft, and that may be, we don't know yet. But because there's stress concentration, well, let's see, we've got what? We've got a key seat on the left. We've got, it's a sled runner, we've got a shoulder there in the smaller section to get to the middle diameter section. And then there's another key in the middle diameter section, and then another step up to a larger section of the shaft all the way to the right. So we have to decide where is the largest stress concentration and figure out the torque capacity of each of those sections, and then pick the minimum. That would be that would be the maximum torque that the shaft can take, because it's kind of like the weakest link in a chain, right? That's where it's going to break. So the sled runner keys, in your text it says the stress concentration factor should be 1.6. For the profile key, let's see, let's do it this way. Let's put it over here. For the profile key, and would that make sense? Yes. Okay, so the section on the left will be here, the section on the right will be here. That will match the figure and the way it's laid out. For the profile key, the stress concentration factor KT would be 2.0. So now we've got two stress concentration factors from the keys. But on the left-hand side with the sled runner, there's what I'll call the small step, because it's in the smaller section of the shaft. And we need a stress concentration factor for that small section. So we need the radius of, at the side of the step divided by the diameter of the smaller section next to the step. So that's 0.188 over 1.25. 1.25 is the diameter all the way on the left. That comes out to 0.1504. Now the diameter of the middle section over the diameter of the smaller section is 2.0 over 1.25. That comes out to 1.6. And so if I use Appendix A22-7, which is the appropriate one for this, then the stress concentration factor, the best I could read off there, was about 1.275. Now notice that both the stress concentration factors occur on the left-hand side of the shaft, and I just need to select whichever one is the largest stress concentration factor in order to estimate the stress and therefore the maximum torque that the section could take. So it looks like I basically wasted my time here, right? Because this stress concentration factor is larger. Let's check what happens in the middle section. So moving to the right in the section I will call the large step. For that portion we need to do the same thing. I need the radius at the shoulder divided by the diameter. Now you have to be careful. I used a lowercase dg over here and here. These are two different sections. I use this terminology because that's what the appendix uses. Notice I'm going to use the same appendix here because this is just another step. Okay, it's just that the geometry ratios may be a little bit different. So all this really indicates is the radius at the shoulder divided by the diameter on the smaller side of the shoulder, whichever that happens to be. Well, the radius here is also 0.188. Now, it wouldn't have to be this way. These two radii could be different because they're in different sections of the shaft. But of course, in a real shaft that's made in the real world, they'll probably be the same because the same tool will probably be used to make both of them. So we'll just, of course, use what they've told us, but that's a justification for why they would be the same. So now this diameter being on the right-hand step, well, the smaller diameter, is the diameter in the center of the section of the shaft that we see, and that's the 2-inch dimension. Okay, when you take that ratio, it's 0.094, and then take the diameter of the larger section at the step to the smaller section. The larger section is 3 inches in diameter, and now the smaller section is the middle, the 2-inch. So that's 1.5. If you take both of these, let's do it this way. If you take both of these to A22-7, what you'll find is that the stress concentration factor, KT, is about 1.40 or so. So notice that this stress concentration factor of 2, which is in the same section, is larger than this one, which is 1.4. So we will use the 2 instead. So again, this really didn't matter. We just had a bit of exercise there, I guess. So let's get rid of the small step and large step. We found that the key is, or the keys are, what are providing the highest stress concentration, so we'll just use them. Okay, now notice we're looking for the maximum torque, and basically what we want to do is, given this material, let's figure out how much stress a torque would make and then compare that and make sure it's not too much. Okay, so that would give us the maximum torque. In fact, the equation I'll use is like this. It's from A22-7 because the equation is the same. It's just a stress concentration factor equation. You take the stress concentration factor multiplied by the torque times 16 divided by pi dg cubed. The 16 really goes down here because this is really, this bit is just 1 over ZP. And again, I can't remember the name of that. I always forget it. I'll have it memorized eventually once I'm used to teaching this class. But anyway, I just put the 16 in the numerator because it's in the denominator of the denominator and ultimately ends up in the numerator. So that's what I did. Now let's rearrange the equation because what we're really interested in is the torque. What we'll do is, given the material, we can figure out what the maximum stress is that material could take. And so then we can rearrange this and solve for the torque. And of course that would end up being the maximum torque because we're going to plug in the highest stress that it could take. So solving for the torque here, I just added the subscript max to make it clear. You'd have the maximum stress multiplied by pi dg cubed divided by 16 kT, where that's the stress concentration factor. Okay, so now let's plug in numbers and see what we get. Now we'll have two different sections, right? We'll have the small step and the large step. So let's make that clear. So small step, in other words, on the left-hand side of the shaft, the maximum torque that section could take would be the maximum stress. Well, we haven't gotten that yet. How can we get it? Well, remember, they said that this is a repeated load, and what that means is that the maximum shear stress that can take would be the yield strength divided by 8. If you look, there's a table near the beginning of the chapter that has these safety factors, essentially. One of this is actually 2 times 4. The 2 is for the fact that this yield strength is a normal stress, or a normal strength, whereas we want the strength in shear. The 4 is the safety factor for the fact that this is a repeated or a fatigue load, which is a very crude way to do it, but for now that's fine. So basically we need the yield strength. If you go look up the yield strength for this material, you find that it's 97 KSI, and then if you take that 97 and divide it by 8, then you'll see that it's 12.125 KSI, which is of course 12,125 PSI when we plug it in for the maximum shear strength. So then pi here multiplied by a diameter, where we're working on the smaller step, that needs to be the smaller diameter, which I've got it here in my notes. It's 1 1/4 inches. So we take that and cube it, divide by 16, and the stress concentration factor for this section, which would be the 1.6 from the sled runner key. Now notice we have pounds per square inch, and then this would be inches cubed. So 2 of these inches cubed will cancel with the square inches in the denominator of PSI, and we'll end up with inch-pounds of torque. So this comes out, when I plugged it into my calculator, to about 2906 inch-pounds force. At the large step, we're going to have the same equation. The only difference is that the size of the shaft is different, right? The smaller section for the large side of the shaft is 2 inches, and the stress concentration factor is 2.0. Okay. Plug that in your calculator and you'll find that this is about 9,523 inch-pounds force. And again, the idea that the weakest link in the chain is going to break tells us that the maximum torque that shaft can take is constrained by the small step, just as we thought it might be. So the maximum torque this shaft can take is 2,906 inch-pounds.